Okay, so we were talking about the trend in homologous series. It's very easy for us to fall into this trap of more carbon, stronger everything, but that's not always the case. So let me take a moment and let me point out this graph first, because this reflects what we've said thus far. It's just a chart I pulled off some website somewhere. I should have given credit, but I didn't, so sue me. But notice that this is simply a homologous series of alkanes, and this is just telling you that the molar mass climbs, and as the molar mass climbs, notice the melting points climb, the boiling points climb. Now we know why. Intermolecular forces climb, okay? But that only explains things like melting point, things like boiling point, even things like volatility. But there is another one, and I've shown it down here. Excuse me, it'll be at the very bottom. I'll just keep it at the top. There is another physical property we need to compare in a homologous series, and that is solubility. So it's a very important concept that I'm going to talk about here. Solubility has to do with polarity, and like dissolving like. You guys remember that phrase? Like refers to polarity. So things that have similar polarities tend to dissolve each other. Now notice that this compound at the top, methanol, has an OH group, which is an indication of hydrogen bonding. What type of intermolecular force exists in the compound water? Hydrogen bonding. Therefore, water with its hydrogen bonding tends to dissolve with methanol with its hydrogen bonding. Like dissolves like. Agreed? Yeah. So, you could say that methanol is soluble in water. They are both polar. Right? But what happens to the polar nature of this compound as the number of carbons increases? Is that making it more polar or less polar? Less polar. So the issue of solubility, you have to really consider what's going on here. As the number of carbons increases, the non-polar character increases, therefore making it less soluble in water, more like something like oil, for example. Does that make sense? So you'll see on a table of solubilities that the solubility of something like methanol will be listed as infinite, meaning it freely mixes with water. It's miscible. Whereas something like this 1-pentanol, you'll find its solubility is fairly low. And if we were to continue to compounds with, I don't know, I'll just say 10 of these carbons in a row, there's a lot of them, then you'd find that it's completely non-soluble. It will not mix whatsoever. Why? Because at the end, it's still going to have that OH group, and you could argue, but you said like dissolves like, Mr. Waggle. But remember, it has to overcome the intermolecular forces between adjacent nonpolar sections. And if the interaction between water, the solvent water, and this hydrogen bonding end, if this interaction is not strong enough to pay for breaking these, they don't dissolve. So do you understand what I'm getting across here? As the number of carbons increases, solubility goes down. Okay? Because it becomes more nonpolar. You all good with that? Yeah, we're good. You sure? Okay, good. Then let's do the last thing, and then we're done for the day. So the last thing I want you to see is the difference between a structural formula. This is a structural formula. It's what we've been doing. Please understand that this shows the H's. It's a detailed version of what we've been doing. This is a condensed formula. So I wanted to show you some of the tricks here. This condensed structural formula that's written here, I'm recreating it so it's big enough for us to see here in class. On the video, you should see it because you can make it full screen and it shouldn't be a problem. But when you see this, please understand that this and this are identical. So there's some rules here. When you see something in parentheses, that can mean one of two things. And the first thing it can mean is like in this example. This means that that thing in parentheses is attached to the neighboring carbon, typically the carbon before it. There are times when it will be listed first, as I'll show you in a second, and in that case, it would be attached to the carbon after it. Now, the thing to keep in mind here is carbon obeys the octet rule. It has to obey the octet rule. So notice here, CH3 this. If you're reading left to right, this is not what it means. Do you understand why that's impossible? There is no such thing as this. Hydrogen cannot violate the octet rule. The H's here are attached to the carbons they are adjacent to. that carbon has an unbonded side. So what's bonded there? That's the next one. CH2. Oh, it's like this, right? Of course not. It's H2. I'll put the H's on just to highlight them. Okay? Now, how many of those CH2s in a row? 3. That's what that means there. There are 3 CH2 groups attached in sequence. Here they are. I'm showing the H's again just to be consistent. We all good there? At the end, OH, which is what we have here. Does everyone see that? Okay. Now another example of this technique is here. Notice, I'll redraw this one. Here the parentheses start the chemical off. But there is a difference here, and I want to make sure you see it. The octet rule still guides us. This does not mean this. Because if we follow the same pattern as before, we connected CH2s to each other. And I said that the first one was bonded to that carbon. So if we apply that rule here, those are bonded to each other. If that's the case, that's done. That would be ethane. Done. This carbon would, that's an H. There's nothing else to put there. CH3, well, there's 3 of them. That would be impossible. How can we put 3 CH3s? Because that is the number 3 right there. How can we put 3 CH3s? It'd be impossible. So you have to understand that what that means, excuse me while I erase this, you'll have to understand that when it's, oops, didn't mean to do that. And it was this one here. Anyway. So when we do that, when they're listed first, you have to understand from the octet rule, CH3 has to be kind of a attachment. It's separate. It's not inside the chain. It has to be outside the chain. So this symbolism, where CH3 with the subscript of 2, that is the 2 individual carbons attached. This is the 2 CH3s here. Sorry, these lines aren't coming on very easily. There's those 2 CH3s. Man, that's sloppy. There's the 2 CH3s here, and they are attached to that carbon, which is there, which has 1 H attached. I'll put it up. It does not need to be up, but I'll put it up. Next to it is another carbon there with 2 H's, and then the OH. Does that make sense? You sure? Okay. If it does, then do me a favor. We've already covered this issue. I'm not even going to go back to it. I want you to write on your note paper the condensed structural formula for the compounds I write in this area. So let me write a couple more. Okay, so write the condensed structural formula of those, and I'm going to pause the video. I'll come 20 minutes, but whatever. Okay, so let's go ahead and see how this worked out. This would be, reading left to right, CH3, this is this group, this is CH2, CH2, CH2. So instead of writing 3 CH2s in a row, which you could do, you could simply put it in parentheses and put a 3, and then at the end, CH3. This carbon here. Does everyone understand how that works? Okay. Down here, we have CH3. That's the, I'll say it's this carbon. It very well could be this carbon, but we'll talk about that hopefully tomorrow or maybe in a few minutes off camera. Let me erase that line for us. So that's that CH3 there. Then we'll do this one. How many H's are attached to this carbon? Good. And then we'll do this attachment, which I'll indicate with the parentheses. And that attachment is CH3. Now I'll continue with this next carbon here, which is CH2. And terminated by CH3. Can I go back to this one? Yeah. Yes, sure. What do you need? How do I do that? Yeah. Well, I'm reading left to right, and I'm indicating branches off of the chain with parentheses. Okay? So this first carbon here, which has 3 hydrogens attached, are not drawn here. They are, you see what you're missing? Okay? So this one on the bottom here, let's go ahead and write that one. Now, this is kind of a trick. If we went left to right, here's what we would write. CH3, that one, CH2, CH, parenthesis, CH3, sorry for the bending here, and then at the end, CH3. Now, this one here? Yeah, that's the point I'm trying to make. These two compounds are actually the same. So I wanted to make that point clear, and it takes people a while to see that. In a minute off camera, I'll show you the models here to prove it. But these two are technically the same, which brings me to my last point. How do we know they're the same? Well, one way, if you're not sure of seeing them, is to name them. Now, before I leave the subject of condensed structural formulas, though, this would actually be acceptable. They wouldn't penalize you. They're not telling you to name it. And you could convert this into this formula very easily. Okay? But I'm here to tell you, you will probably never see this because it does not reflect the name of this compound. So let me be clear about how do we name compounds like this. This is actually a different category than we've seen before because we saw alkanes with a straight line and it was very simple. But here things are a little different. So let's name these. First of all, the top one. The top one is 5 carbon alkane. What is that called? That's pentane. That's very simple. There is no number because the only functional group is the alkane, which is indicated in the suffix. So there's no need for a number. 1 pentane makes no sense. It's just pentane. But here, what do we call this? Because our rules say we have to identify the functional group, which is alkane. Next rule, how many carbons in the longest chain? And we look, what's the longest chain of carbons present? 4. But the last thing we need to consider is, are there any functional groups or attachments or branches? I snuck that phrase in yesterday. I don't know if anybody heard it, but we have to count a branch as a functional group. So I'll demonstrate. If we numbered these carbons, let me clear off this little red part here. If we numbered these carbons, we'd have 3 choices for carbon number 1. This one, or this one. And we're looking for the longest chain of carbons. So that eliminates here to here and here to here. Would you all agree? That's only 3 long. So now we have 3 choices for longest chain. Here to there, here to there. So we have 4 choices. Here to there or here to there. Agreed? Which do we choose? Because it matters. The answer is the same answer as when we numbered functional groups. We start with the end closest to the branch. These ends are closest to the branch. The branch occurs here. But which carbon do I choose? It doesn't matter. They are equivalent in chemistry. Now, I'm going to pause the video. Okay, we're back in the video, and I'm going to do this very quickly. When we name these, we are going to treat the branch just like a functional group. And so we're going to start numbering from the end closest to that branch. And I just went through with the class in person how each of these carbons is identical. So I'm just going to start from this one for reference sake, making this carbon number 2. And therefore the branch, which we are treating like a functional group, is on carbon number 2. So just like with the functional groups, I indicated the location of the branch with the number 2. And in this case, the functional group is one that we don't recognize. It's a carbon with 3 H's. That is known as a methyl group. The prefix for one carbon is meth. The YL indicates a attached group, so it's a methyl group. This is 2-methyl. Now we name the longest chain, butane. Here's another one. Yeah, I'll go fast. Okay, 5 carbons is the longest. Here's a branch on carbon number 2. 2-methyl pentane. Do you understand? We'll pick up there tomorrow.